It's a pleasure to be here. I technically retired about 1.5 years ago, and this is the earliest I've been up in about 16 months. Forgive me, I actually work about half-time. I still have a couple of research projects at the University of Wisconsin, so I go in, but I go in on my own choosing, and it's been such a pleasure that I tell friends I should have done it 30 or 40 years earlier. But anyway, I'm going to talk about robotic barn design to improve dairy calf and cow health. And I'll admit first right off that I primarily have worked in more conventional housing, freestalls, milking parlors and such. But we're getting some experience in robotic systems, but we're really going to try to apply what we've learned in conventional housing to robotic systems. For those of you from elsewhere in the world, I live in Wisconsin, highlighted in red here in the US, and it's a northern tier state, central. We tend to deal with a lot of extreme cold. And that affects some of the items that I'll discuss later on. I also will approach things from a health perspective because I came out of veterinary school in the mid-70s. I spent 12 years in private dairy practice in the Midwest, and then joined the University of Wisconsin in 1989. And so there'll be health orientation. And I did some research, and then clinical work was never treating single animals. It was investigating herd-level problems of calf health and cow health in the industry. So it's a herd perspective with a health orientation and a fear of winter. Okay. I'm going to talk about 4 topics. I'm going to emphasize calf barn topics. There's approximately 1.5 hours here. Probably the calf barn topics are going to take about 1 hour. And I'm going to emphasize ventilation and drainage, and then some other building structure things. Then I'm going to shift over and talk a little bit about ventilation around robotic milking systems, because I think that's an area of a great opportunity to improve robotic milking systems. Then, because of the importance of lameness and minimizing lameness in robotic milking systems, I'm going to talk a little bit about freestalls. And then I'm going to close out with some aspects of transition cow health as we wrap up this session. So I'll come back to the slide to reorient you periodically. So I'm going to talk about calf health and designing calf health facilities to maximize or reduce or minimize the risk for disease processes. And this is a photo taken in an automatic calf feeder barn that's been up for about 2 years now. And I would suggest that this is perhaps the most successful calf automatic feeder barn that I know of, and I would contend it's as good as anything on the planet. And you'll see a number of features here, and we'll come back and close out this session with this barn in a little more detail. There have been some over 400, maybe 500 calves that have gone through the system now. They've lost 1 calf, and they had a post-mortem done on that calf, and it had a congenital heart anomaly. Anyway, it's an extremely successful facility. I'm going to begin by saying, coming at it from a conventional point of view, I'm going to say at the beginning that it's difficult to improve the environment for a baby calf beyond a hutch. And yet our industry has been moving away from hutches very aggressively in the last couple of years. And so I'm going to say it again. We don't think we can do much better than a hutch, but we can do as well as a hutch for the calves, and we can do better for the caregivers with a barn. This statement came to me from a dairyman, and he said I had a choice. I could either keep my hutches or I could keep my wife. And in this case, you'll see that he kept his wife and constructed a hoop barn in the background. But the issue in Wisconsin, when we've seen this tremendous growth from a transition from 50 or 80 cow tie stall barns to 300 or 1,000 cow freestall barns, is that 4 or 5 calves on milk was one thing, but 40 or 50 in our winter is a whole different game. And so there's a number of reasons why we're seeing the interest in calf barns. And the weather outside is frightful. I am an academic guy, so I have to have a citation for everything I've got here. That's a well-established reference anyway. But then the recent information about the importance of growth in the first 50 or 60 days on adult cow milk yield means we have to approach a kilo of gain a day during those first 50 days. And that's almost impossible to do in a hutch in our winter. And then we're starting to feed 3 times a day and making the life of the caregivers that much more miserable in the middle of the night and sloshing milk and water. And anyway. Then automatic calf feeders is almost exclusively a calf barn issue, not suitable for hutches in our weather. And then in the last 5, 6 years, a number of our dairies have experienced calf health equivalent to that of hutches in barns, provided they're designed appropriately. And I think this has given impetus to the tremendous interest in calf barns in our state in the last couple of years. As I shaped this presentation, I wanted to focus on risk areas for calf disease. And I'm going to say that one of the first primary risk areas is the risk for diarrhea or enteric disease in really less than 2 weeks of age. Then there's a second risk period for respiratory disease that starts at about 20 days and kind of runs throughout much of the nursery period but tails off toward the end. And then there's a new risk right after weaning. And usually to do with social stresses of new environments and new numbers of calves. And probably that's reduced in your automatic feeder barns, much of the social stress after weaning, but it still is a bit of an issue. And I'm going to come at these in more detail, but as I'm going to focus on things that I would advise you as dairy families to look at in calf housing, I would emphasize, number one, using drainage beneath the bedding to make a drier bed to reduce the risk of diarrhea or enteric disease. Second, I'm going to be talking quite a bit about ventilation, but introducing clean, fresh air from the outside, regardless of temperature, into the microenvironment around the calf. That's not ventilating barns. This is ventilating the area around the calf. Third, we're going to try to deal with whatever air comes into that ventilation system, no matter how cold it is. We're going to try to deal with it and avoid cold stress by using bedding or blankets, but rather than other methods. Then by the fifth point down, we're going to try to minimize the exposure of the youngest calves to the oldest calves. And so we'll be dealing with all-in, all-out housing if we can, usually limiting the range of age to about 2 weeks, 2.5 weeks of age spread within any one barn, if that's possible, or within any one pen. And then we're going to try to reduce social stress at weaning. So the first, I'm going to deal with a number of topics here. I'm going to talk about a field study of calf barn respiratory disease risk factors that I conducted about a decade ago that changed my view of ventilation and calf housing entirely. Then because of that, I've got a picture of a naturally ventilated barn, but there's these positive pressure tubes. Then we're going to talk about we like to utilize natural ventilation as completely as possible. It's green, it's environmentally friendly, there's less mechanical parts, there's all that. But there are going to be some deficits of natural ventilation that we're going to try to compensate for. So I want to spend a few minutes on limitations of natural ventilation. Then we'll be using these tubes, and I want to distinguish them from what I'd call old generation tubes of the 70s and 80s. And then some comments on drainage, and then I'll show you one example barn. So Our Wisconsin industry was being reconfigured. It's been always being reconfigured, but a very aggressive change from stanchion tie stall barns to freestall barns in the 70s and 80s and continues. And dairy families would build new naturally ventilated cow barns and like the results, and then they'd build naturally ventilated calf barns, and these are some series of calf barns. And as a problem investigator in the 80s, 90s, we started, a colleague of mine, Sheila McGurk, and I would investigate calf barn problems of endemic respiratory disease in naturally ventilated new barns like this. And I would check with the engineers on our campus, and they would say these barns meet the standards for natural ventilation. And yet we'd go inside and we'd see high levels of respiratory disease with all kinds of pen configurations and open mesh pens and solid sides and covers and all that. But we had an endemic respiratory disease as though we had unventilated barns. And so I got a bit of funding and we mounted a field trial. And this is Dr. Alfonso Lago. He was a young veterinarian from Spain. And he worked with me in that winter, and we were on a different calf barn every Tuesday and every Thursday through the winter of 2004 and 5. And we looked at all kinds of building factors that might affect the rate or the prevalence of respiratory disease in these barns. I like to point out that he's holding a tulip planter. Some of you will have planted bulbs. And it wasn't that we were planting tulips in these barns. He was taking core bedding samples, and he'd take 5 bedding samples from at least 15 pens and to sample dry matter, for example. So we were looking at all kinds of things that could be risk factors for respiratory disease. One of the things we worked with quite a lot was air quality and in the barn and in the pen. And this is an impaction type air sampling device. There's a little fan in there, a little motor, a little computer chip to control the speeds. And the little red plate is growth media. So you put that growth media plate on the machine, put that cover on top, turn on the fan, and you'll take a sample of a fixed quantity of air. Okay. Then we'll incubate that plate for a number of hours. And so I've got some standard values here. If we go outside, on a typical day, you'll have somewhere between 100 and 1,000 CFU, that's colony forming units per cubic meter of air. If we go into a well-ventilated designed room, mechanically ventilated, much like this, I've been standing here looking at the ventilation inlets here and such, we usually be under 2,000 colony forming units per cubic meter of air. Really, really high quality air. There was very little standard information at the time, but I would wade into naturally ventilated cow barns, big Holstein cows everywhere, and we were usually under about 15,000 CFU per cubic meter. And then when I started sampling these individual calf pens, our first samples we couldn't count. You'd have moved a couple of 10 or 20 liters of air and couldn't count the samples. They were so overgrown. But they were clearly in the range of 5 million and higher. And so we had to recalibrate instruments to get down to a sample where we could count, get a reliable count. And basically, if we get to 25,000 CFU per cubic meter in an individual calf pen, that's really as clean as it ever gets. But usually it's a matter of 100,000 or 500,000 or many millions. And so scientifically, we don't worry about 1,000 or 2, but we talk about orders of magnitude. And we're not at 100, we're not at 1,000, we're not at 10,000, but we're frequently at hundreds of thousands or millions. That's 4 to 5 orders of magnitude in terms of pollutants. They're incredibly polluted places. Most of these bacteria, there's a nasty sample in the upper left. Most of these bacteria do not cause respiratory disease directly. They're usually Staphylococcus and Streptococci and some other airborne, mostly that's coming off of the skin of calves. But there's emerging science that if you have a tremendous load of these non-pathogens, they still are inflammatory to lung tissue as the lung deals with clearing those dead organisms. So, but we're going to just say they're a marker of how polluted the air is in the pen. When the study was done, there were 3 key factors that were associated with improved respiratory health. And this was all done in single pen calf barns in our winter. First was higher quality air. Lower airborne bacterial count was important. Second, nesting. I'll talk about a nesting score in just a minute, but this ability to provide a nest in winter conditions in Wisconsin was a key factor. And third, a solid panel between each calf was a major protective factor for minimizing respiratory disease. And this is going to be important because I think as any of you look at automatic feeder barns, we're immediately going to group housed calves. So that solid panel is gone. And that means to me that we're going to have to do a better job with clean air, with providing bedding or bedding and jackets, doing a better job with colostrum and with feeding, because we're going to give up that 1 unit. Okay. We'd arrive on these calf barns, and when this trial was done, virtually all of our calves were underfed milk. So they would all get up and be looking at what's happening. Maybe they'll feed us. But in an hour or two, they'd settle down, and once they'd start settling down, like that calf on the right is laid down, we would go around to the clipboard and say, if we can see the hoof and the hock, that's nesting score 1. The calf is above the bedding. If the hoof and the hock are partially obscured, that's score 2. And if we couldn't see either the hoof or the hock, that's score 3. And this is how it affected respiratory disease. So we'll spend a minute on this graph. On the horizontal axis on the bottom, we have airborne bacterial counts times 1,000. So the range runs from 27,000 up to 1/3 of a million. Very dirty air at 1/3 of a million. On the vertical axis, we have the prevalence or the percentage of calves with respiratory disease, running from 0 to 70%, whatever. But let's go right to the middle. There's a fine at 177,000 CFU, pretty dirty air. If those calves were in deep nesting, score 3, we'd expect about 24% of the calves to show signs of respiratory disease. And we had a specific scoring system we went through to determine that. If we had the same dirty air, but the calves are lying on top of the bedding, score 1, we'd expect about 52% to have respiratory disease. So this nesting in our winter conditions, this deep depth of straw, was hugely protective against respiratory disease. Okay? Said another way, we're going to talk a lot about ventilation, but we can go from filthy air at 300,000 to 27,000 and drop the prevalence of respiratory disease about 30%. Or we can take the same filthy air off on the far right, and the difference between having deep bedding and nesting score 1 and nesting score 3 is about 30%. We can do as much with bedding in Wisconsin as we can with air quality. Okay. The solid panel was surprisingly protective. And you'll commonly see, if you look through calf barn ventilation publications, you'll see statements, well, mesh dividers makes it much easier to ventilate a barn. And there's no question that that's true. But the panel was protective against respiratory disease. Here's the same graph, air quality on the bottom and the percentage of calves or prevalence with respiratory disease on the vertical. Let's go to the same mid-quality air, 177,000 CFU per cubic meter of air. If we have a solid panel between each calf, we expect 20% to show signs of respiratory disease. But if we have a solid panel between each calf, we'd expect 45% of the respiratory disease. It's just a major, major protection. Okay. So I'll come back to that in a little bit. One of the big points here was that the service alley air quality, the samples taken in the middle of the service alley were statistically associated with a calculated barn ventilation rate. And we measured air speeds hitting the building and angles and all that stuff to calculate a theoretical barn ventilation rate. But the air quality in the pen had no association to barn ventilation rate. And said another way, we can ventilate barns, but that's an old-fashioned concept. Ventilating barns is simply, that's something from the last century. What really counts is to ventilate the space around the calf. And it's a profoundly different thing. Shifting gears just a little bit. We looked at factors in the barn that we could use to reduce airborne bacterial density in the pens. And the colder barns had cleaner air. The larger the pen, the cleaner the air, the lower the stocking density. And thirdly, having fewer solid sides in the pen improved air quality. So we had a confounding factor. So the solid panels reduced respiratory disease but raised airborne bacterial counts. So we started thinking from this trial, how could we keep the panels and improve the air quality between them? And I looked at a number of options, and it looked like positive pressure tubes might be the most feasible way to do that. So hence the direction. So this is where we somewhat ended up. We have a naturally ventilated barn. This is on an extremely cold February day. And there's a curtain sidewall with an opening. There's an opening right there in the middle. There's an open ridge. And then there's a positive pressure tube up above that runs, that never stops. And we use that system to drive cold air from the outside. And on that particular day, it was about 8 degrees below zero Fahrenheit. And we're going to design tubes to deliver a whisper of air into the pen of each calf and have it arrive at the calf at what's called still air. And still air is defined as air moving at about 60 feet per minute, or about 1 foot per second, so 1/1000. If it's less than that, it's considered to be still. Okay. So I'm going to talk next a little bit about limitations of natural ventilation. Why should we supplement natural ventilation? And I have to take a big gulp, because I taught principles of ventilation to our veterinary students for a quarter of a century. And I look back at the first 20 years of notes and lectures that I did there, and we made the most of natural ventilation. And yet, I clearly didn't understand what I was talking about. Someday you too will be humiliated by things you've written. Anyway. We look at what's happened in the US, in North America, and more in the last, I would expect that we're well over 5,000 calf barns in North America that have been refitted with these positive pressure tubes. And it's been done without an advertising campaign. It's been one testimonial of one dairy family to another who've driven this thing. And they typically will say that calf pneumonia treatments are reduced by half to 2/3, half to 3/4. I've been working with a group in Germany in the last couple of years, and they've been keeping records. There was a question from here, I think from somewhere, but the German government has an active program to reduce antibiotic use in agriculture. And in these 62 calf barns, the number of calves treated for respiratory disease has been reduced a little over 60%. So, same systems, okay. And all this suggests that our naturally ventilated calf barns were not being optimally ventilated, okay. So very briefly, a primer on natural ventilation, and why would these tubes possibly be as successful as they are? Natural ventilation is driven by prevailing winds moving directly into eaves or open sidewalls and into the building. And then secondly, when it goes over an open ridge, And Jeff Bewley talked about an open ridge and that sort of thing. But as it goes over an open ridge, it creates a slight lift or a slight negative pressure draws some air out of the building. If there is no wind, we talk about thermal buoyancy, of where the animals in the building will warm the air, warm air will rise and leave the building, which causes it to go out and the cold air would be drawn in. Okay. So let's look at that in more specific terms. Here we have a naturally ventilated building with an open ridge and some open eaves, and there's a wind coming up to one side. So if that air is colder outside than it is inside the barn, that air will hit the building, some will go in through the eave, some will whatever, animals will warm it slightly, it'll go up, the ridge will provide an opening where air going over the top causes a draw, and it ventilates really quite well, much of the time. Here's a graph. I don't know how well you can see that, but this is, I think, 14 days in January of 2011. It's in Fahrenheit, so I apologize. I have the same graph in Celsius, but this is a predominantly Fahrenheit audience. So we're looking at a green line and then a red and a blue line. And the red and the blue lines are interior temperatures in two separate calf barns on one site. And then the green line is exterior temperatures. And so on some of the coldest nights, they're looking at minus 10 degrees. And you'll see other peak minus 8, minus 1 or 2. But very cold at night. The sun comes up, and that outdoor temperature goes up dramatically. It hits highs of 25. In one day, it hit 32 or 33. Okay. But the important point here is that there's a period of 3 to 4 hours every day where the exterior temperature is warmer, the sun is warming it, and the exterior temperature is warmer than it is inside the building. Okay, 3 to 4 hours every day. So now we have a wind coming up against the building. We have yellow arrows, so it's warmer outside than it is inside. So what happens to natural ventilation? We ventilate the barn, air goes in, but it's warmer than the air inside, so it tends to come in through the eave and go on up and out, and you have very little mixing with the polluted air at the level of the calf. Some of you have sat in the back of say a van with no ventilation in the back seat. It's only 3-4 hours. Anyway, that can be an eternity, quite frankly. Okay. And then there are periods of time where there is no wind. And then we count on thermal buoyancy of animals warming that air and causing it to rise and ventilate. And in Wisconsin, this is in every airport in the US, there are charts generated of wind roses like this that give the directions and the speeds of wind coming into a location. But in Eau Claire, Wisconsin, in January, it's calm 9.75% of the time. So it's another section of time where there's no wind. And I already showed you graphs where the interior of the barn is colder than it is outside. Those calves aren't generating enough heat to drive a natural ventilation system on thermal buoyancy. It is dead on these days. So let's just say that when there is no wind in a calf barn, we end up again with an extremely polluted environment. And I think that's the issue. Here I've got some fog going into a positive pressure tube, but I think that's really the issue. I think natural ventilation works well most of the time, maybe 80% of the time. But these tubes are set up so they run 24/7, 365 days a year. They deliver a small amount of air into the area around the calf, and I think that's the reason why we see the respiratory effects that we do. Okay. I'd welcome questions at any time if anyone, I think that's one of the goals of the conference organizers, is to turn this into a conversation rather than a lecture. But so if anything comes up, I got one.
So how do you get past the fact that you're introducing external air that's hotter than the inside of the barn, even with the tube? How how do you force that air down?
The question is, how do you actually get air that might actually be slightly warmer, those few hours a day where it's slightly warmer than in the interior, how do you get it to the calves? And that's a whole issue of tube design. The air comes out of the tubes at maybe 6 meters per second or 1,200 feet per minute. It comes out high speeds, and it has enough velocity that it is driven toward the calves themselves. So we're going to talk a little bit about that in just a second. So, I'm not going to do much technical aspects of it today. I'd like to say, number one, these are new generation tubes. They're not the tubes that were widely used in agriculture in the 1980s. We're going to use these tubes to supplement natural ventilation, but not recirculate air. And in the 80s, almost all of these were recirculation systems. We're going to have them run nonstop, and we're going to just accept that it's very cold sometimes, and we're going to deal with ample bedding, blankets, jackets, stuff like that. And then I won't dwell on this, but there are technical differences in the way we are designing the tubes now versus the ones that were done in the 70s, in order so that we can achieve a uniform discharge of air along the entire length of the tube. And secondly, we're going to, as you asked, we're going to drive the air toward the calves, and then to avoid subjecting the calves to a never-ending draft, we have some technical calculations to figure out how far it takes to reach still air. I like to say I'm now the world's repository of photos of failures, of tube failures. I get them from everywhere. This happens to be a barn in Ohio where they'd installed tubes, but they'd done it the old-fashioned way. These are high-quality materials, but there are three cardinal rules that are being broken here. Here they located the fan so it mostly recirculates air from inside the barn. There's a louver up to the right that theoretically should let some fresh air in, but it's recirculating air, ensuring that any calf that's sick, it will recirculate that air and distribute those pathogens to every other calf in the barn. Secondly, there are some fussy things about fluid mechanics. This tube will create uneven air distribution along the length. You'll have very poor air discharge coming out of the holes nearest the fan. So probably the first 30, 40 feet get almost no air from this tube system. And most of the air comes from the distant end. And fourth, these holes are oversized, and they're pointing toward the calves, but they're too large for that system, and they will create a never-ending draft on the calves below that tube. And that's not such a big deal if you have a group pen, but sometimes if you have a calf in a fixed location and they can't move out of that draft, that becomes an issue. Okay. So the first thing, we're going to take this fan and move it away from that wall and move it into the wall so it's 100% outdoor air, clean, fresh air. Then I'm going to have very few technical points, but we're going to size the fan appropriate to the room. We're going to measure out the room, and we're going to change the air in that room 4 times per hour, approximately. And so that means you have to fit the fan to the room that you're going to use. Then third, a second point, we're going to fit the diameter of the tube to the fan to achieve uniform discharge. So the tubes have to be fitted appropriately for the fan capacity. And then we're going to size the holes, the diameter of the holes, to achieve a certain throw distance. And so these things have to be custom fitted, because some tubes will be 5 meters high, some will be 2 meters high, and that changes the throw distance to the calves. So everything has to be done custom to the barn. I'm already getting into this. If we put up, the tube needs to fit the fan, and the fan must fit the room. The height of the tube determines how far we're going to throw air. And then, depending on how wide we're going to throw air, determines where you put the positions. They're described in terms of clock positions, like at 3 o'clock and 9 o'clock or 6 o'clock or 3:30 or whatever. But depending on how far we're going to throw air to the sides will be determined by a clock position. So here's a automatic feeder barn with natural ventilation wide open for mild weather. It'll be mostly closed in cold weather, and there's a positive pressure tube system that never stops, that ventilates on still days and in winter days where there's no wind or whatever. Or those hours every day where it gets warmer outside than inside. But it's got 3 rows of holes, and so the clock positions are they're chosen to deliver a blanket of fresh air across the entire width of the pen. The next picture will be of another tube system with 4 rows of holes, and you'll see larger diameter holes because we're going to throw air further to the sides than the ones that go straight below. So it's a custom job. I'm making that point because a number of companies are now trying to make one size, may have 5 options of tubes, and it's simply not going to work as well as it could. This is a spreadsheet we've developed at the University of Wisconsin. We've taught some over 300 people around the world on how to use this system. There are other systems that can certainly work, but maybe the point would be that it needs to be done well. It needs to be done well to achieve what you want. And we have a lot of information on this Dairyland Initiative website. I think I've got one more slide showing it. It used to be limited to dairy farmers in Wisconsin only, unless you paid a fee. But in the last, Dean Foods has funded access for dairy farmers across the United States. And then about 6-8 months ago, Saputo has funded access for dairy farmers from around the world, free access. And they're funding a translation into Spanish and French over the next year. So, and this thing gets updated and changed at least weekly by various staff at the UW. These tube systems are going into all kinds of barns now. This is a weaned heifer barn. These heifers come out of hutches, go into a wean barn. But we've measured nice reductions in post-weaning respiratory disease in spite of having an open front that's, what is that, 15 feet of open front, and yet you can measure improved air quality at the level of the calf in these barns with these tube systems. Then we worked with a lot of retrofitted old tie stall and stanchion barns that have become calf barns. And here's a calf barn that, I won't dwell on it, but it had exhaust fans and inlets, but it never, ever could deliver fresh air into the individual calf pens. It's simply impossible at low winter rates. Here's a picture of the same space, same view, retrofitted with positive pressure air ducts driving small amounts of air at low speeds in between each panel. Okay? So it's infinitely flexible. Approximate cost. Fairly low key, fairly low cost. I'd say it's almost always cheaper than a tractor tire. The fan usually $250 to $800 typically. The tube and cables usually about $7 to $50 per linear meter. What is that? Between $2 to $2 to $18 per linear foot, depending on the range of materials. Power cost, if we take a typical 20-inch fan consuming about 500 watts, that's usually about $450 in the Midwest annual operating cost. So it's a modest, modest thing. Reducing respiratory disease by, say, half easily pays for this. There are benefits in terms of weight gain. There's benefits in terms of labor and such. In our part of the world, there was tremendous fear of cold. And I know there's a number of people from Canada here, and Canadians are fearful of cold. Did a comparative trial with 2 identical barns, one with a positive pressure fan tube system, the other one without. But both were naturally ventilated. I already showed you some graphs from this farm. We ran loggers for 2 weeks. And here's a picture of the calf barns. The one on the left has got a hood up in the center hooked to a positive pressure tube. The other one now has a tube, but it didn't at this point. Inside, again, you can see the positive pressure tube in the top of the one, and the other one is not. Otherwise, they were identical. Same naturally ventilated openings of eaves and such. And cutting right to the chase, left column, north barn with the positive pressure tube, then there's the south barn without the tube and outdoors. And if we look at temperature, average temperature of the bottom line, 23 degrees over 2 weeks, 23 degrees in the barn with the tube, 23 degrees the barn without the tube, and 17 degrees outside. There was no difference in temperature, but there was probably 1.5 degrees colder at night in the barn with the tube and 1.5 degrees warmer in the day with the tube. Amplitude was just a little bit wider. Okay. Again, this is a barn in Wisconsin that is using geothermal ducting, buried pipes to warm air that goes into a positive pressure tube systems in a calf barn. And again, some of you may be interested in it. They actually have 3 little huts like this where air enters the hut, and there are pipes, flexible plastic pipes that go down. They're buried 7 feet down. They run about 200 feet to the barn. There are actually 6 buried pipes. Air comes up in the little shed on the outside of the barn where that air is collected from the pipes, and then it goes up into positive pressure tube systems. And we are currently monitoring temperatures of air going in and coming out. We'll be doing it year-round, but in the middle of the winter, it looks like you get a bigger benefit on the coldest days from geothermal tempering of air, probably about 15 degrees Fahrenheit. And it might also cool the air a little bit in the summer, but anyway, we'll be measuring all that and tracking that over time. The dairy owner of this said, "This is a gift that keeps on giving." Okay, I'm going to shift over and move away from ventilation, talk a little bit about drainage and such. I look at all of the calf barns that I've seen in my lifetime where we house calves on a concrete floor, and I view them all as a mistake. I view concrete flooring beneath the bedding without drainage as a risk factor for enteric or diarrhea diseases. And because we use long straw frequently, but we put long straw on concrete, long straw absorbs urine fairly poorly. Many of you will know you use long straw on concrete and the liquids run right out. So many people will put down shavings or sawdust as a base beneath their calves, and then they put straw on top of it. And that's to keep the urine from running. But then that sawdust becomes a big wet sponge. And I made the point that we sampled on the bottom in that field trial, we collected 975 calf core bedding samples, and it had a mean dry matter moisture, average dry matter of 48%. That's silage, it's at least alfalfa haylage kind of moisture. And we're putting calves, laying them down in the middle of our winter on a bed that's 48% dry matter. And we can do better. We have got to get the liquids out of that bedding. But it's more than that. When we put bedding on this concrete, we already talked about soaking it up, but then frequently liquids run out, move out of the bedding, and if the calf has diarrhea, urine goes on top of the diarrhea feces, and then the liquids move out, and then the calf caregivers step in it, and we track it everywhere in that barn. And then we try to control disease, anyway. What can I say? Nice system of drain, but every time the calf caregiver steps in, we are moving stuff. So we're going to really push for various systems to move liquids away directly out of the bedding. Have long straw or something that doesn't hold liquids. Have liquids move into gravel and then into drains. It depends on local ordinances about how you have to collect liquids from calf barns. Have it moves directly down. And then the central work alley. Typically work alleys are located, they're sloped to the center, to a center drain if it's a concrete floor. But we would rather slope it toward the calf pen and either move it directly into the the gravel, if that can be done, or have a separate drain, but not running water into a central work alley. And we would, in general, advise more sweeping of the central work alleys and less washing. So typically, they'll usually build a base of about 1.5 feet of gravel, coarse gravel, with a 4-inch drain tile to carry liquids to the outside. Each time when they clean the pens, they'll remove a little bit of the gravel and replace it. And depending on the cleanliness of the bedding of the straw, if there are lots of fines, you may need to remove the entire gravel thing annually. But if it's a very clean, long straw, you can usually go 3 to 4 years before you have to remove the gravel. Some people have put landscape fabric over the gravel to keep it clean, and that works nicely. It allows liquids to go down, but then you have to sort out the landscape fabric from the straw or the bedding when you clean it, and some people tolerate that and some people don't. The basic point is that dairies that have experience with both systems will say they'll say they use half the bedding to achieve an equivalent bed. When we've looked at the numbers, it's actually they'll use about 60%, but anyway, it's a major reduction in bedding. So here's a picture of an individual calf barn. Has gravel and tile beneath the calf pens, extremely dry beds. If you go to that website, you can see videos of people when they clean the bedding and how all that sort of stuff is handled on that dairy. Finally, I'm going to shift toward the importance of all-in, all-out housing. Our group has met with a lot of people planning calf barns in the last half dozen years. And many people will arrive with plans for a great big calf barn, and will usually really not think we had a successful meeting if they leave with plans for a great big calf barn. We're going to try to move towards small, all-in, all-out units. To try to minimize the transmission from older to younger calves is one factor. But secondly, the ability to wean, say, all calves from one barn at one time and then clean it and let it rest for a few days, preferably up to a week, but just a few days rest with a positive pressure tube system helping to dry the thing out is powerful in breaking salmonella outbreaks and things like that. Okay, I'm going to close out the calf barn section by having another look at this particular calf barn and show you how this incorporates some key features. The things we're going to try to incorporate are spatial allowances of some over 30 square feet or more per calf, a bedded space per calf, not including the service alleys. Secondly, we're going to have deeply bedded surfaces. When weather is under 50 degrees, I forget what is that, about 10 Celsius, something like that. We're going to have drainage beneath the bedding. We'll have multiple all-in, all-out barns with downtime for cleaning. We'll have natural ventilation supplemented with positive pressure tubes and very minimal sidewalls so that in mild weather and warm weather we can completely open the sidewalls and allow natural ventilation to occur. Okay. So here's a picture of that, an automatic feeder barn. There are actually 4 rooms. You can see 2 rooms here on this left side and one of the third room on the far. And a common service room. It's an H-shaped barn like this. Again, there are going to be 1 service room serving all 4 rooms. On each pair, they're completely separated rooms in the middle. Here's a picture. There's 1 entrance into the milk room. The door on the right is open for all other reasons today. It's empty. But the point is to try to have all traffic going through 1 room through foot baths. Okay? If we go into the room, you'll see foot baths to each of the separate 2 of the calf rooms. There's calf feeders and doors to the left and to the right. And behind the camera, there's another 2 rooms. This is a room that's being filled with baby and neonatal calves. Newborn calves go into the individual pen for an acclimation period, and then when they're acclimated, they go into the feeder pen. And then as the pen gets nearly full, all these individual calf pens are removed, they're cleaned, and then they get it set up to start in another separate room. Very efficient use of space. The floor is sloped. It's a 2% slope to the central drainage, and then there's gravel and tile, and then liquids are collected in this particular dairy in a central collection point. And then, again, natural ventilation, open sidewalls on both sides, split curtains, and they use natural ventilation as fully as possible, but you're looking at 3 sets of positive pressure tubes. The one in the middle is a small system designed with a small fan that's designed to change the air in the room 4 times per hour. And that one never stops. Never, ever stops. Then there's 2 additional ones that are used, in this case, for other purposes. And they're controlled by thermostats. And so as the barn gets warmer, actually there's also wind control on that too. If it's windy, they don't come on. But if the winds are slow or non-existent, and in an 8-shaped barn, there's going to be, depending on wind directions, the central work alley interferes with the winds to some part of the other barn. So each one is controlled individually. And if it gets still and warm, one or both of these other supplemental fans come on, and you'll see very large holes. The one on the lower left has got huge capacity holes. But there we're not trying to achieve still air at the level of the calf. Those are designed to achieve air speeds moving at a little over maybe 250 feet per minute, enough that on a still day that those become the fly control in that barn. They will disrupt, make it unpleasant for flies. Anyway, I'll just say it's a very successful barn, and we have virtual tours of this barn and things on that same website that I referred to earlier. That website, sorry. So I'm going to wrap this up and shift over to a couple other topics, but I'm going to make the comment that positive pressure tube systems allow us to deliver fresh air to a calf, and we start ventilating the space around the calf, which is the critical issue in calf barn ventilation. In our part of the world, we're going to accept very cold air and deal with that air not by stopping ventilation, but by use of bedding, calf jackets. And those of you, some of you may work with Jersey calves. In our climate, Jersey calves have a difficult time in our winter. And we would advocate the use of infrared heaters and sometimes tempering air, as in the geothermal technique and things like that with those situations. We're going to really push for drainage beneath the bedding to improve both the nesting score, moisture control, and the such, and reduce the risk of enteric disease. I'll make the comment that if you have individual calf barns, which really is not the topic here today, we have moved away from having every calf having a solid panel, but we have every other calf have a solid panel with mesh between, because there are some benefits of social benefits, the calves learning to interact with each other as a pair prior to weaning. And then we're going to try to do all-in, all-out groups in automatic feeder rooms or whatever kind of barn to reduce disease risk and allow you to clean and dry a building before you reuse it again. I'm going to move on to another topic unless there's other questions at this point. I expect there'll be opportunities for questions at the end as well. Here's one.
I was just kind of wondering, and when calves get raised in room temperature, is that beneficial to that calf, or is it like in preheat the air?
Is the calf being raised at, you say, room temperature?
Yeah, Celsius.
You mean at
like warmer environment? Does that help that calf over being in a 3 Celsius? Because that's what we're fighting.
It's a complex question. We have experience with calves being raised in warm nurseries and then transferred to cold weaned barns, and that's a major stress.
Right.
And I personally, there are exceptions here, but I personally have an aversion to warm calf barns Because my experience, based on more than a handful, has been that if we have a warm calf room, several issues. Ammonia in the air becomes an issue. Ammonia is very volatile at warm temperatures, but not volatile at cold temperatures. So we have more issues with ammonia and other issues. Secondly, the cost of heating air to room temperature on most farms is such that we end up in getting engaged in a discussion of how much can we reduce the ventilation rate to minimize the heating costs. And when we accept cold as cold, we ventilate lavishly and accept the cold. And so I personally have an aversion toward warm nurseries. We tend to have more airborne bacterial density. That's showed up in our trial. And so there's quite a few reasons why, philosophically. Now, you can get them to go well, but that's a whole complex discussion.
I wanted to know, what do you think about warming the concrete?
The question is about warming concrete, and that can be very attractive. Again, it provides some thermal comfort. It clearly does. The barn where I showed you the two graphs, over 2 weeks at a time, they actually had warm concrete in those barns. So I'll just leave it at that. It's a local warming effect, yes. If I had a choice between having drainage or heated concrete, which one would I choose? I would choose drainage. Oftentimes you have an option for both, though, because usually the pens are not completely drainage. If you have deep gravel and it's too big an area, you put a skid steer in it, you'll get your skid steer stuck. So there are things like that. So usually there's part of the floor will be concrete. You could have some heat there.
Hey, Ken.
Yes?
That local barn that local barn you mentioned does not use the heating tubes anymore. They had trouble with some bacterial growth, so they don't use that part of it anymore.
Okay, I didn't know that. We have a local knowledge here that this is the barn with the, show the picture. So, yes, yep.
They don't use it anymore because of some bacterial issues.
Okay, okay,
So to answer your question, drainage is way higher than
okay. Okay, I'm going to move. Any other questions? I'm looking at some really bright lights here. I really can't see any of you in the back here. Okay. I'm going to move along and talk a little bit about applying the same technology to robotic milking areas. So, ventilation issue in cow milking facilities. Okay. So I like to say that these tubes allow us to place air, fresh air, exactly where we want it at exactly the speed we want. And I'm currently finishing up some research projects in holding areas, with conventional holding areas. And I'd love to go there, but I'm not going to spend really any time on that, other than to maybe make a couple comments that apply to robotic systems. Robotic systems, we do not have the stress of large numbers of cows confined to a small area. But I do think that as I look at the robotic milkers that I've visited over the years, they usually are poorly ventilated. They usually are the most poorly ventilated areas in your barns. So back to conventional holding areas. Each one of these cows is putting out the BTUs equivalent to a typical office space heater. About 1,500 BTUs, anyway. And if you put 300 of these, if you put a room with if I put 300 little office space heaters in this space and turn them on, that's the equivalent amount of heat that is being generated. And we are currently working with a trial where we had vaginal thermometers, temperature loggers, and accelerometers on feet and such. And we have a publication that's in the works, but cows tend to accumulate heat while standing in these holding areas, and it's a major, major risk factor for heat stress. Okay. Traditional holding areas are usually dependent on natural ventilation for fresh air. We're counting on prevailing winds to drive air into those holding areas. And natural ventilation will be compromised by adjacent buildings and utility rooms and still days, just like calf barns. And when natural ventilation is compromised, we have these recirculating fans in there, but recirculating fans recirculate. And so those of you who have waded into the holding areas know that that sometimes is just an incredibly hostile space. And I want to make the point that having a fan creating air velocity with recirculation is only velocity. It's not ventilation. I showed you this graph earlier. Oh, this is a different one. This is July in Dane County, Wisconsin. Prevailing winds are predominantly from the straight south and a little bit from the southwest, occasionally others, but overwhelmingly south and south-southwest. So we'll go to, this is a dairy, top view of a dairy, north-south, and we've got a little holding area with a little yellow spot up there, and we have winds coming from the south, and south of that barn we got a whole bank of silos and a great big cow barn, and somehow natural ventilation is supposed to get in there and ventilate that holding area. Stop it, it ain't happening. And then we hang fans around, and the middle of these holding areas get hotter and more humid as the day goes along. This is the primary heat stress risk area for most of our dairies. Maybe I'm a little bit beyond there, but on a lot of dairies, this is the primary heat stress area. So we've been, based on the work with calf barns, we started thinking maybe we could use these same systems to deliver fresh air, guaranteed fresh air from the outside into the holding areas, no recirculation. That air would be a lower temperature and lower humidity. And the key is maybe humidity in a holding area where we're evaporating water off of wet cows. We're going to take one fan and convert it into 25 to 50 small air jets. We're going to distribute those air jets throughout the holding area. And in current holding areas, there's not hard science, but there's a lot of anecdotal information that boss cows take up positions in holding areas under the most attractive fan locations. And the subordinate cows get marginalized to the hottest and the ugliest parts of that holding area. Okay. And then we're going to have a vertical airstream from this tube coming straight down that goes around the cow. It's called porous airflow in fluid mechanics terms. And it's going to do that rather than skittering across the backs, and little shorter cows in the middle of bigger cows get no horizontal air movement and all that stuff. So just a couple of pictures. This is a dairy we worked with starting up, although we retrofitted quite a number of these now. But this is a new planning where they were going to have 350 cows in a holding area. So we made a proposal of tubes taking fresh air from the outside, put them into the holding area, and ventilate that area. So here's a picture of that holding area of cows entering. And there's a bank of, I think, 18 tubes, I think 350 cows coming into this thing at one point. Very large holes to create air speeds of 400 feet per minute on the backs of the cows. So that's a cooling airspeed, 2 meters per second for those of you in metric units. Another picture, and again, it's distributed. Every cow will usually have somewhere access to about 2 to 3 discharge air jets somewhere on her body, head, whatever. And you can walk into the middle of this thing, and it's as comfortable as a May day. Unless it's not May. It'll be as comfortable in the middle of that room as it is outside, whatever that day is. Okay. Then palpation rails in this particular naturally ventilated barn. There were a couple of palpation rails, so we made a proposal here for supplemental tubes in that area. And again, here they are. And it becomes, you have fresh air coming in at appropriate speeds. But I want you to think about these tubes to deliver air at certain speeds around a robot milking unit, okay? And then the rotary parlor, again, sometimes an issue. And again, we made this proposal and they installed it. And here's 2 fans, again, with tubes that come up, and they're big air jets coming down. And so as those cows rotate, they're in hot weather, they're always under an airstream 400 feet per minute on the backs, fresh air on the backs of those cows. And there's tremendous options, again, to deliver air where you want. Now, robots. I'd like to think that the robotic milking unit should be the freshest, most attractive area in your barns, a place that will attract cows. But when I visit robot milker units, usually the floor around the robot is very wet. Usually the air in and around the robot is frequently quite humid and stale. And the robots, by their nature, obstruct any horizontal movement of air, whether it's natural ventilation or wind tunnel or cross-ventilated. So here's a robot, and again, you see the solid sides, 3 sides of it, opening on this side. Here the fan has been installed to blow air away, but that air, there's quite a bit of science been worked out as to where air is drawn into a fan, and you'll be as likely to draw air from right below the fan up and around as you are from over here. And I guarantee you there's nothing coming out of that. That fan has nothing to do with, with air quality in that room. So, and we can set these up. I put this windrows here. Again, if we had winds from the south, this room office interferes with air movement into this area. If winds coming from this direction, we have total obstruction here. The barriers here, these are barriers to those, you know, and it's just part of the nature of robots. They obstruct horizontal movement of air. So I'm going to suggest that this is a great opportunity to improve the quality of air in and around the robotic milker units, where you can deliver how much air you want at the speed you want. And so I sketched over this thing, and you could have a tube coming from wherever you have access to fresh air, and you could size the holes. You could size the holes so you deliver high-speed air if you wanted to cool cows in that area in the summer. You could, depending on the nature of the fan and the size of the fan and such, you could drive some air to clean and dry the floor below to reduce the potential for slippage and such. I could tell stories, but I'm not going to take the time. But anyway, all of this is just extremely feasible. And you see, you could set this up as a cooling thing in the summer with, again, high-speed air at the level of the cow. If you didn't want that in the winter, you could switch it out so you could have a different tube, same fan. You could unhook that worm gear, unclip your cables, and place it up with a different tube with different holes, and that deliver air that's still air at the level of the cow, but still ventilates, but to avoid draft. Or you could keep the same air, and you could draw air out of your utility room, warmed air, and make this a warm, slightly warmed air in the middle of the winter. Again, I think there's all kinds of possibilities. I'm going to go on. Talk a little bit about freestalls and lameness. Question. The question is, are there estimates on how much milk cows lose going into conventional holding areas? I'm not aware of those. Forgive me. We know that when cows stand up, they lose body temperature in the summer. When they lay down, they gain body temperature. And the temperature changes start when a cow lays down, and that's why cows are standing more in the summer. When they lay down, their body temp starts to go up within 2 to 3 minutes. It's going up. Hence, they stand so much. But they go, normally when they're standing, they're losing, they dissipate body heat. In a holding area, they usually are gaining heat because of the thing. But how much it turns into milk, I'd have to make a bunch of guesstimates. We could try that, but I don't have it today. So there's the wrong color robots, but you can see if there's a problem. There's some fans blowing, recirculating air out in the barn, but prevailing winds, that'll be the most poorly ventilated area in that barn. There's just no question about it. But let's move on. However, I made the comment that I wanted to point out that lameness is a critical issue. And again, I'm going to rehash an old issue that sand-based stalls, either deep sand or sand over a mattress, is the biggest single thing in confinement that we can do to reduce lameness. Sand, I'm going to say, in Wisconsin, my colleague in 2003 did a survey of barns, didn't know it at the time, did a survey of quite a few dairies. He scored locomotion scores on 35 dairies, summer, did it again in the winter. And the mattress barns, the mattresses was the biggest single factor related to lameness rates in our industry. They had 1.7 times the lameness rates of sand-based barns. Then a Minnesota survey in 2006. Mattress barns, 28% cows were lame, sand barns 17%. And it's more complex than that, obviously, but it's the biggest single risk factor that we see in our industry related to lameness. Nigel Cook and I did this study, it's more than a decade old now, where we looked at why do we have this sand mattress difference? And we found 6 mattress barns and 6 sand barns. They'd all been in place for a number of years. They had identical fixtures for stall dividers, dimensions and such. And we scored cows for locomotion, and we didn't have locomotion. Here I've got bar graphs. On the vertical axis, we have hours in a day, 24 hours in a day. We'll just talk about it a little bit. The purple bar is lying time, that cow on a mattress, locomotion score 1. The purple area is 12 hours lying. The blue-green is time standing in the alley, about 3 hours a day. Then the pale blue is time feeding, which is about 4 hours in a day. The green, the olive green, is time in the milking parlor, a little over 2 hours. And the red is time standing in the stall. That's the first bar. That's locomotion score 1. Locomotion score 2, a cow walking pretty good, but just with a slight arch. Not clinically lame yet, but score 2. She stands 4 hours a day. And the locomotion score 3 cow, she's walking with a head bob and an arch. And she's standing 6 hours a day in the stall with reductions in resting time, in feeding time, and in alley time. The parlor stays the same. Okay, locomotion score 1, 2, and 3. Now let's take a look at the same graph on sand. Locomotion score 1, 2, and 3. We'll see that on deep sand, behavior didn't change. And we're going to contend that when a cow gets to locomotion score 2 and a large, that's not a lame cow. It's just a little gimpy. There's many reasons cows get to locomotion score 2. On a mattress barn, their behavior changes and they start standing in the stall 4 hours a day. And that slows the recovery rate. And we think that's the key factor as to why the prevalence of lameness in our mattress barns is almost double that of sand barns. Okay, doesn't have to be deep sand. We think deep bedding of any kind can do it, but it has to be more than the little dusting of shavings on top of a mattress. This is a pack mat design where we have the mattresses are buried, are going to be going in here. So, and put on, say, more than a couple inches of bedding above the mattress. So here's some mattresses ready to be slid into that location. There they're being fitted in, and here's a cow on that buried mattress with bedding. There are several advantages. Number one is the cows can't dig deep holes. You can manage it more consistently and such. But again, my colleague did this study on this kind of a style, on a pack mat, the mattress below the bedding, and I'll show you that compared to another surface. Where here, again, locomotion score 1, 2, and 3, all got 13 hours of resting time and less than 2 hours a day stall standing time. Pretty finely graded, slight increase with more stall standing time, but still less than 2 hours a day with minimal disruptions. Then if we go to locomotion score on a mattress with the typical modest amount of dusting, we see the same conventional locomotion score 1, 2 hours a day standing time. When they go to locomotion score 2 or 4 hours a day, almost 5 hours a day standing time. And on locomotion score 3 on the mattress, again, 6 hours a day with reductions of all these other things. And so Again, it brings home again the critical point of having a couple inches of bedding, not the dusting that we typically have on a mattress barn. With the deep bedding, deep sand versus, say, the pack mat approach with a couple inches, owners say they use about 50% of the sand over the mattress compared to the deep sand. So anyway, I'm going to move along. My target is to finish up here in about a little less than 10 minutes. So
just a question on that.
Make it fast. No, go ahead.
10 years old, right?
Pardon me?
The study originally was done,
Yeah.
It's approximately 10 years old.
Yep.
Have you included or has anybody redone the study looking at some of the new technologies in what the mats are? And with 6 hours of standing time, when I walk the barn every 3 or 4 hours, I should be able to see that and see a cow standing for 6 hours. Would I not notice that?
We know that the mattress technologies have changed a lot. And I'm not aware of current studies, more recent studies on those directly. However, the idea of picking those cows out standing by walking through a barn is really hard to do. That's been done with video, time-lapse photography, and that sort of thing. And we were stunned. I personally put in between 400 and 500 hours watching cows videos, and it's stunning what we see with that technique versus real life walking around barns. But you may have skills that I don't have.
I doubt it.
Yeah.
Dr. Nordlund, we do have until noon, so you got plenty of
Wait,
time.
what?
We have until noon for questions and stuff like that, so
Okay.
yeah. We have 15 minutes.
One
built
little
into
segment
the-
left. I think it's about 8 to 10 minutes, or maybe
Yeah.
less.
So take your
And
time.
then we'll have more questions. So, question, go ahead.
For those that have mattresses already, and different reasons, because sand is great for cows, but sometimes in different countries or conditions it's difficult, right? And treatment and all that.
Yep.
What can they do to make their mattresses more comfortable to their cows, so that we can bring a better well-being to the cow? That's the reality. Many people still have.
We think that the issue is depth of bedding. And like if you can put some alternative bedding on top of a mattress here, we think you can probably achieve, again, I've not seen any efforts to do that on research, but a couple of clinical things suggest that other bedding, shavings, manure, dried solids, things like that, the critical thing is the depth. And if you could if you already have mattresses that are in good shape, if you could, well, take jackhammers and break out the concrete, set them down a little bit, and have a sufficient depth, my clinical opinion was that you would have major improvements in lameness reductions. But any loose, friable material going on top of that we think should be equivalent to sand. Okay, I'm going to close out on key factors on transition cow health. And I'm going to be heading toward the feeding space, the idea that feeding space of the pre-fresh cows is the most important thing you can do to minimize fresh cow disease with facilities. There are many interesting things with robotic herds milked by robots. We're used to having cows coming out of a parlor as a group, and we want a certain amount of space for all, because they're all going to eat as a group when they come out in batches out of a parlor. But you don't have to deal with that pressure in a robot herd, so that I think that frees up a lot of potential demands for feeding space. And I realize there are some serious questions here, but it's not as critical as it is in conventionally milked herds. But your pre-fresh cows are not going through your robots. Your pre-fresh cows are traditional group, and when you feed cows, they come up as a group. And anyway, I'm going to take you through a little story that, as a veterinarian interested in fresh cow health, that we developed a transition cow index, and that led to field studies, and it opened my eyes to the importance of housing and feeding space to minimizing metritis, RPs, ketosis, and such. Okay. So key factors for transition cow health. Very briefly, out of frustration with clinical health records, many dairy farmers here, some of you will have varying different qualities of health records, and yours may be excellent, but they're not the same as the excellent records on another farm, and they're not the same as the non-existent records on other farms. Anyway, we got so frustrated, I moved toward the idea hit that we developed a transition cow index where we use fresh cow milk as a marker of fresh cow health. Basis, sick cows produce less milk. And the index was patented in the US in 2008 and in the EU in 2014. We developed mathematical models from 500,000 cows, from 4,000 dairies, to predict what an individual cow will yield on her first test date. It's based upon her prior lactation milk and how long her dry days were and the month of calving and how old she was and that sort of thing. Then this transition cow index is the difference between what she actually produces at first test and what we predicted. And there's actually 4 variations of this index, and some of you will be familiar with it in one format or another. There's English and metric, and there's different kinds, but bear with me on the concept level alone. We have all these factors, whether they're on POSLAC or not, and prior lactation length, and whether they aborted or not, but all of that stuff will go into a mathematical model to predict how much she'll yield. And if she beats it, it's a positive transition cow index, and if she misses it, it's a negative. And we've done some studies that relate various diseases to ups or downs, okay? And so here's a graph from a dairy farm, and this is over 1 year at a time. The dots are individual cows arranged by calving date over a 12-month period of time. Here are the most recently calved cows here. And so here are cows that hit 0, and that means that they milked exactly what was expected on first test date. And that could have been projected at 105 pounds, and they made 105. We could have projected her at 60. It depends on what her history was. And, but they hit it exactly. And here's some cows that missed by 26 kilos or 50-some pounds under what we expected. These are usually extremely sick cows. And here are cows that exceeded expectations. Okay, but this is a herd orientation. This is meant to look at the quality of transition programs, not cows, okay? So at the herd level, this herd over the last year averaged 0.5 kilo under what we'd predicted. And when we go to this is the Wisconsin Dairy Ag Source clients, the ranges, there are individual herds where the average cow over a 1 year period of time misses our projections by 12 kilos at first test. There are other herds where individual average cow beats, over a 1 year period of time, they beat our predictions by 9 to 10 kilos. So that's a 20 kilo range on first test, 44 pounds difference we're going to attribute to transition cow management. But anyway, we took this data and then we did a stratified random test where I had an associate that identified herds in this area and 10 herds here and 10 herds here and 10 herds here and 10 herds here. And I didn't know what the scores were. We went out and we tried to look at what are the factors that the farms were doing to try to sort out what affects transition cow health. For perspective, when we did this, we were entirely focused on rations. Ration formulation, ration feedstuffs, energy levels, calcium levels, transition cow nutrition. Okay, so we did 50 freestall dairies in Wisconsin, stratified random selection, and I'm just going to move along. This was funded financial support from Pfizer Animal Health at that time. Okay. And we reviewed routine management practices. We gathered a lot of cow level data, condition scoring. We looked a lot at nutrition. We reviewed pen moves. We looked, oops, sorry, I'm getting twitchy up here. I also keep looking at my clock, but I'm told I should relieve the pressure on that. And I did an extended herdsman interview to learn how they screen cows and looked at treatments of certain conditions. Okay. When the stats were done, there were 5 factors. First of all, feeding space. Feeding space. Second, freestall base, strong advantage for sand. Freestall area, larger size freestalls were associated with improved fresh cow health. Moves to calving pen, if they went into a calving pen at 2 days or less before due date, was better than 3 or more days in a group calving pen or a solo calving pen. And then the screening method, we sorted into 4 categories, but herdsmen or herdspeople who looked at attitude and appetite did better than dairies where they were almost routinely using thermometers only. And there were plenty of dairies that had no systematic screening program. So, very briefly, rations. When we did this trial, we thought it was ration formulation. And yet, this is our graph of herd average transition cow index. 0 is about industry average. Here's about 50 dots, 45 dots. The herds with the lowest, poorest transitions here and highest here. And this is graphed against close-up ration NDF, essentially high straw diets over here. 45% NDF in the pre-fresh diet. 32% here. And this is as flat a regression line. This is a shotgun blast. It's as flat a regression line as we can make, suggesting that ration didn't have much to do with it. Now, we think we know better than that, but this isn't a powerful test. And so the things that emerged as statistically significant were bigger factors than ration NDF. So bunk space. And out of this, we came out with the recommendations. We're going to have pre-fresh bunk space so that all close-up cows can eat simultaneously. And for a number of reasons, we're going to push toward 30 inches of space for a pre-fresh cow. I'm going to skip the other things. All of our headlocks, or I shouldn't say, probably 94% of the headlocks in the US are 24 inches or 61 centimeter on center. And they are not sufficient for Holsteins to eat. We've done a number of video studies, and these will fill to a max of 80%, or 4 out of 5 headlocks. 1, 2, 3, 4 filled out of 5. And that's standard, except on palpation day when you force cows in. So we've been pushing for 30 inches of feeding space in a pre-fresh pen. And if you've got, these are some updated headlocks that are 76 centimeters or 30 inches each, and they're great. But if you've got 24-inch headlocks, that's fine. Just have 5 of them for every 4 cows. And we will do more to improve fresh cow health with that than any other thing you can do in your transition cow management. So then the question comes in, how big should the pen be? We have space per cow, that's one thing, but the number of cows in a pen changes. And so I went through the planning booklets for books, and they always went through our system like this. They said, okay, if we're going to have a pre-fresh pen, a close-up pen for a 1,600 cow dairy, the mathematics would say, how many calvings would we have for a week? Well, 7 days is 1.9% of the year. 1.9% of 1,600 would be 31 cows per week. Then they'd say, how long are they going to be in the pen? 3 weeks. So we'd say 3 weeks times 31 cows per week, build it for 93 cows. And by definition, that pen is overstocked half the time and understocked half the time. And with adverse fresh cow health effects half the time. And so we pulled records from about 30 dairies where we had good records in Wisconsin. We went through our seasonal calving variation, and we made the recommendation that if we calculate the average number of cows per week and multiply by 130 to 140%, we will have an adequately sized pre-fresh pen. And I think that you should go through similar things. Even if you go to have a robotic dairy, you still feed all your pre-fresh cows at the same time. I could pull out other slides that suggest that cows, that if they can't eat simultaneously, they eat less, and that affects fresh cow health. But I'll leave that for another time or another day. So am I soon done? Yes. I'm going to say that of all these factors associated with transition cow health, I'm going to suggest that bunk space in the pre-fresh pen paired with soft surfaces under large stalls are going to be the biggest factors you can do to reduce the rates of ketosis and metritis and DAs and such. And right now, we're almost a decade down this trail, and we've got a vast number of stories of people who've made these investments and changes, and we believe it works. So as I wrap up, I'll call attention to that website one more time. I think you're going to get copies of these slides. And I'm going to say that if you have any questions about any of these topics, calf barns or stalls or transition cows, I'd welcome them at this point.
Thank you very much, Ken, for the great presentation. So any questions?
Yes, I have one. Thank you. I just want to go back to the robots, and you had mentioned that the area in front of the robot is one of the worst ventilated areas in the barn. And I've been involved with robotics since about 2002, and that's actually the first time that I've ever seen that air tube out in front of a robot like that. And to me, it looks like a great idea. Actually, I wish I could go back to my area where I live and say it was my idea, but I've already tweeted it out, so I can't do that. But, you know, I'm just curious. You had it drawn in, so I'm assuming it's just a concept, but do you feel that if the air quality was better in front of the robot, whether there's an opportunity to even get more milkings out of the cows per day because they come up to that area more often and then go into the robot to get milking? So possibly adding 0.1, 0.2 milkings per day because of better air quality in front of the robot.
I'm not aware that any exist. I've talked about it a little bit, but again, I'll just say we've been working on these holding areas, and that's really very recently. I think it's the first ones I went in 3 years ago. I think there were 2 holding areas, conventional holding areas fitted with it. We watched them for a while, and we mounted a research trial. But anyway, so that's still a very new concept. But from what I learned about calf barns, it sounds simplistic, but I'm done with the idea of ventilating barns, and I'm all about ventilating spaces. Okay, and back to calf barns. One of the first things dairy farmers say after they install a positive pressure tube system in a calf barn, they'll say, well, I don't know anything about calf health, but we used to feed the calves, wash up the center alley, and the alley would be wet until 2 in the afternoon. And we put in a tube, and now that floor is bone dry by 10:30 in the morning. And I see Nico nodding your head, and your next speaker has a lot of experience in the same concept. And so then I think about, I mean, you're ventilating the barn, you always did, but now you're getting air to particular locations, okay? And when I look at robots, and I think most of you can take me to school on robots. I'm no expert on robots by any means. But I look at robot installations and say, just the barriers, that's an area that, in spite of good ventilation in the barn, that's going to be a troubled area for ventilation. And so you're not behind. I think the idea of taking tubes to push fresh air in is still a pretty new concept in agriculture, but they give you tremendous flexibility to do so. And then if you learn how to size the holes and that sort of thing, you can have the speed that you want. And again, I think, I mentioned before, I think that on a bitter cold day, I would think you could make the robotic area, cows like warmth too. We know that, and you could temper that air and have a little more warm, fresh air in that area. I could envision getting higher usage rates, but that's all speculation.
Nico.
I like what you bring up as an idea to make positive tube ventilation in front of the robot. Actually, I was talking to some guys last week. Sorry. Yeah. I was talking to some people last week, and my idea, Ken, and I like to know
if I might interrupt.
Sorry.
This is Nico, your first speaker this afternoon. Is that right? Yeah. And with tremendous experience in the Netherlands.
So, my idea was, or my question to you is, do you think that a small positive pressure tube inside the robot room would be even better, because you create a stable and more a less humid climate in that robot? And I think, if I know, because I know the system pretty well, we work a lot with it, flies is always a problem in robot houses, right? So I want these flies to get out. They don't need to live there. They go out and live somewhere else. Maybe they can find a company with the animals of Jeffrey and go somewhere else. But what do you think of that?
All very reasonable, and I'd suggest that it depends upon the imagination of people like you to do that. And I've tried to find research as to peer-reviewed research as to how much air movement is annoying to flies. I haven't been able to find anything, but we have a clinical feeling from cow cooling and holding areas that we get into 250 feet per minute, which would be 1.1, 1.2 meters per second. That's about sufficient that flies will find alternative areas. But that's a subjective judgment. But yeah, if you could create that velocity in the room, yeah, I think it would do a tremendous job of that.
And even in climates like yours or in Canada, if it's really cold in the winter, you could also use warm heat or warm air for if you put it in the robot house to keep the robot defrosted in the wintertime.
Yep.
So I look forward to talk about it with you. Okay.
Great ideas, and that's the idea, right? The idea here is we're bringing knowledge forward, and we're thinking what others are not, because probably are not as interested as we are. And as I said, there are no books about this stuff outside, right? So it's where we really generate the knowledge and so on. There is another question from Jake, but well, he comments that very often when we design these robotic dairies, and we have these special needs pens or sick or cow handling pens, they are on the back of the robot rooms. And if you think about it, very often we go to these dairies and are the poorest ventilated areas in the barn, and it is where we handle the sick cows. So there is, of course, a huge opportunity to start implementing this kind of system so that we go in favor of that cow that really needs the help. Jake.
All right, I just have a couple things. One of them is just kind of highlighting on what you guys were just talking about. We're already using positive pressure ventilated air from the utility rooms in the winter to push to our robot rooms to keep them warm. And then in the summer, that air is also used to keep the flies out of the inside of the robot rooms. So that seems to work very well. The second thing is I am going to put pressurized tube or fans in my holding areas this summer, all 4 of them. So I'm kind of excited about that. And I've got a little kind of something that I've learned just in this last year about going back to the calf barns and calf health relating to like first lactation heifer performance. And so right now in my barn, I've got heifers that are calving or have calved in the last 4 to 5 months that were survivors of the winter of 13-14, which in Wisconsin was, I think, the coldest winter ever. I'm pretty much convinced. It started in October and it didn't end until June. and we had record snow, and it was just miserable. And I mean, it was, you know, my calf barn is not the best, and we've made a lot of changes, but basically the calves that suffered through that winter and put so much energy into staying warm versus growing, right now in the 100 to 140 day milk range are performing at about 8 to 10 pounds less per cow per day than their calf counterparts that were born, you know, 6 to 9 months ago. That, you know, were born in the summer and had a chance to get up to, say, weaning age or out to the bigger barns during that time period. So there is a huge correlation between calf health, respiratory issues, and first lactation heifer performance.
Actually, Jake, this afternoon, Dr. Bob James will touch on that point of what is the importance of daily gains on calves and the impact of milk production in the first lactation and so on. So it's very important to keep in mind that first a healthy calf, then we feed them right to grow, and then we have very powerful lactation cows. But if we have used the genetic potential, but we don't have all these things in order, it's just useless. Yes.
Just a quick comment. It's 70 degrees where I'm from today. You see any use for the tubes in just to establish local ventilation in these big open barns that we use?
The question, I guess you did have a microphone, didn't you? It's 70 degrees. Where are you from? Georgia. Okay.
You keep talking about, we use ventilation, we use air movement to cool that.
Yep.
That's what we use it for.
Yep.
We're still talking about a local area where the calf can lay down, that we have ammonia and dirty air.
Yep.
Can these tubes, and I'm sure there's somebody else in here from a warm environment somewhere.
Australia.
We get a lot of question a lot. Well, these tubes are impressive. Can we use it to cool our cow barns, our big cow barns? And yes, you can. How many of you have been to World Dairy Expo in the last year, 2 years? Anybody? The New Holland Pavilion. I got involved and I worked with the engineers to design that thing. But I think they have 2,800 adult cows in there with positive pressure tubes. And I think the exhibitors will, the World Dairy Expo board, for example, has gotten letters from exhibitors who talk about how they shake out straw on opening day and they are no longer spending the night trying to deal with plugged sinuses and respiratory disease issues. But it can be done. But the World Dairy Expo barns had a $26 million budget to build those facilities, and it's costly. Massive tubes, massive fans, and that sort of thing. When we start taking this technology to calf barns, we're usually doing 4 air changes per hour, not 40 to 60. And if we have to take things to 10 times the capacity, it gets to be formidable. And then if we take it to cow barns, it's hard to get a long run. We can get, if we're going to cool cows, we're doing it in holding areas, it's hard to get a longer run with the currently available, commonly available tubes, more than about 50, 60 feet before we need another supply of new air. And so it becomes infeasible for most large dairies, or large dairy cow barns for summer cooling. It's a long way around, but I've spent quite a bit of time to try to, it can be done, but I think it's out of the range economically. So I think you're better off. If you're going to do mechanical systems, the existing mechanical systems are going to be lower cost and probably as effective. But I think in adult cows, you can use tubes to bring in cow barns, to bring in a little bit of fresh air for little local areas, local troubled areas, like around a robot milking system, things like that.
Just to add a little bit to what Bob was saying.
If you can turn it on, Dr.
Just a little bit to what Bob was saying. We just built a robot barn for our calves, and we actually added fans on the prevailing wind side to kind of accelerate that only during the summertime. But what it's done for drying that facility has just been tremendous. This was to supplement the tubes that we had in that facility. And that really, I think, helped things tremendously where we had a warm weather situation.
More questions?
What's the effect of humidity on those tubes? Does that cause any issues? 'Cause I think that
Maybe here, repeat the question.
What's the effect of humidity on those tubes? So like in his area in Georgia, it's very humid as well. Are you going to have any condensation or anything like that?
In general, we're going to say that cows, anytime you have cows in a facility, they're going to add water to the air. And so outside air will almost never be higher in humidity than inside. So the idea would be your fresh outside air will be of lower humidity, lower relative humidity than the inside air. This gets a little complex, but your comment about condensation, so in general, we're going to be almost always reducing water content if we take outside air and put it into a certain site in the barn. If it's 100% relative humidity outside and 100% inside, I mean, you're no change, but in almost all other situations, it'll be lower. Condensation is an issue when two things, where it's very common in the winter, where you take air that's extremely cold, put it into a tube, and put it into a barn that's slightly warmer. And oftentimes, if in the winter, if the barn is much warmer inside, it's usually underventilated and very humid, and then you get condensation on the tubes. And so there are two issues. We're going to try to increase the ventilation rate with that, and then you can have the tubes treated with anti-condensation effects, which are a bunch of little holes on the tube that essentially surround the tube with a little layer of colder air. So I don't know if I'm getting at what you're after or not, but.
Well, what I'm after is, can you use these in like a Florida, Georgia, the areas where there's really high relative humidity? Can you use these?
Well, they clearly don't dehumidify the area, but it'll make the interior temperature and humidity at least as low as it is outside.
Okay, one thing that I would also like to add is very often, and Nico, I think you will address that, but when we combine your presentation and when you combine Ken's presentation, very often we see robotic dairies that spend millions of dollars and a lot of time on designing the lactating cow portion of the robots. But very often we forget about those dry cows, those close-up cows. We house them in the old barn and we don't pay any attention to that. Then we come to these beautiful robotic dairies, and then we start having low production in some cases. And then the farmer complains, what's going on? And they always point, let's go and let's look at the robot. What's going on with the robot? Because it's very easy to point that new thing that you bought that is in the barn. But then when we say, let's look out of the robot, let's go and let's check the basics. Far-off cows, close-up cows, fin bucket space, and all that. We find a surprise that I would say almost in more than 50% of the cases, that wasn't even considered when we think about this project. So let's think about these points, because as we want to get more potential out of those cows and those robots, everything starts with a very good pre-calving period within that transition period. Other very nice area of potential for further development, and we have discussed this, is how we train those heifers before they come to the robot so that they can really take off the right way.